Hi, class. I hope you are all doing well. And I know it's week 8, and we've got our next class coming up, so I don't want you to feel too stressed about anything. There's not going to be a pre-class assignment for our last course. And the final course project, the short write-up and analysis of your own data set, that's not going to be due till the end of the term. So I don't want you to stress about that. I'll send out an email tomorrow morning, but I want to make sure you have the solutions and a little bit of exposure as to what we're going to be doing in our final class. With that, let's get started. I think looking at some of the early results that you've submitted, everyone had a pretty good handle on this assignment. I'm really proud that you were all able to manage handling some of the skills that we haven't touched upon in the past few weeks. So the first thing, I forgot to do a little bit of data cleaning, so I just want to give a fresh script that cleans up some of the issues that I know was a source of confusion. So what we do, we load our data, we drop our residual, and the first thing we're asked is to assess whether or not males or females have a higher temperature change. The narrative behind this data set is, again, we are looking at the impact of a drug on a couple of different outcomes. The primary one we do in our first exercise is whether or not, based on the dosage of the drug, did an individual have an allergic reaction? The first is, based on the dosage of the drug, to what extent did the person's temperature change? How much did their fever increase or decrease? The other outcome is whether or not they have an allergic reaction. So the first thing we do is we have this question of whether or not did males have a higher temperature change in this drug trial, and that is just a standard t-test. We do it. We see that male are indicated by a 1 in this case, because it's a dummy variable. We see that there's a difference of about a half a point, and that the associated t statistic that we're looking at is, let's see, where's it? -10. Our associated p-value is 0, so we reject the hypothesis that men and women, or males and not males, have equal temperature changes in our population sample. I then ask you to do that as a regression, and we should see the almost identical results. The one thing that is worth being aware of is that the way we code data makes the interpretation changes the sign of these numbers. Being a male still corresponds to a 0.546 temperature difference, but the order in which they are coded in t-test it's negative. But all of the results in these interpretations are the same. The one thing where you might necessarily prefer the t-test is when you do these sort of sample mean comparisons. You can see very easily what the interpretation of each sample mean is. That the average for men is 0.88, the average for not men is 0.335, and with a regression model, as we talked about before, this is an additive relationship, so that the interpretation for what the predicted value for not men is 0.335, but the prediction for men is 0.335 plus 0.546. With that, we can go through, we can generate residuals. I want to show you this command for a couple of reasons. The predict command is quite flexible, and you can generate a ton of related output to a regression. You can You can predict the linear prediction, you can predict the associated standard errors, as well as other types of post-estimation procedures that we're not going to have too much of a chance to get into. But I just want you to be aware of these options because there's a lot of useful toolkits, including some plots that you might find helpful. So I've been having you do these plots manually, but you can also do a residual versus fitted plot specifically. So there are commands for that are also nice diagnostics that you can use. So let's add that into our code as well. And you can do it either of these ways. But the takeaway is that you can see that there's, because we only are regressing two things that are predicted value, we only have two fitted values, and our residuals can vary quite a bit within these two fitted values. Those are the things that you should take away. I also ask you to generate R squared. There are a couple of different ways we can do this. The first is we can do a regression, but I also wanted to show you that we could calculate this ourselves, so it's not a particularly hard or complex set of operations. That it really is just a ratio of variances. So what we can do is we can take the standard deviation of our outcome variable, that's temperature change, and we can take the standard deviation of our residual, that's the how much is our model missing, and we can generate this R squared with this formula where it's just 1 minus the residual sum of squares over the total sum of squares. And when we list it, we will get exactly the result. We were exactly the same result as if we had run a regression. So I think that's really cool. But if you ever find yourself in a situation where you don't necessarily have data, you are capable of doing these sorts of calculations so long as you have your predicted values. And I think it's just nice because it gives you a little bit more intuition. The next piece that I asked you to do was to generate a random uniform variable. And you could have done a normal variable. And what I want you to take away from this exercise is just that R squared, that metric that we've been talking a whole lot about, even when you add random noise, R squared is mechanically going to go up. And that's because you're just adding an extra parameter that can help explain a little bit more of the variance, even if it's just noise. The only situation where adding a covariate won't improve fit is when it is an exact duplicate of the covariate you've already added in, and that will just ultimately end up being dropped from your model. Whether or not your adjusted R squared ends up increasing or decreasing when you add in random noise is a bit of a coin toss. Sometimes it will increase your score, other times it will decrease your score. But the takeaway is that you want to be parsimonious about what you add into these models potentially. Next step, we're asked to impute a polynomial of milligrams, and does that improve the relationship, the predicted relationship in temperature change? We can do that really quick. And if you use this C dot milligrams hashtag, you have a couple of nice affordances. One of which is that you don't need to type in the number of coefficients, the same number of terms as often, so that we don't need to write milligrams milligrams, and then the interaction, we can just write it all as this one expression. But I think the real value, and we can see here that the R squared is quite good, that is around 0.9. We're explaining 90% of the variance. That suggests to me that while it's not necessarily an explanatory model or the true data generating process, it does seem to do a pretty good job of explaining all that variance. And the other thing that I always recommend is just to plot things. So when we plot, I really like bin scatter as a command just because it's a nice way to quickly visualize things without having to do too much customization. When we plot the relationship between dosage and temperature change, we can see why this linear regression does a pretty poor job, all things considered. That there's clearly this polynomial curve with the relationship between dosage and temperature change that a little bit seems to help reduce temperature, but after about 100 milligrams or so, temperature change increases. There are a couple of things that I do want to emphasize that while I might occasionally be sloppy and use causal language here, that doesn't necessarily mean that there's a causal relationship here. It could be that, for instance, individuals who need more than 100 milligrams of this drug are just generally sicker. And as a result, they would tend to have higher fevers or maybe even really higher fevers than what's currently being reported in the absence of not receiving the drug. So it's just a general limitation. But looking at a regression, we can see that we do a pretty good job explaining this fit. The next thing I ask you to do is sort of estimate what is the marginal effect of increasing dosage at different points and at different points for distinct patient characteristics. And for that, we can use this margins command, where we effectively take the first derivative with regards to our regression and we test at 0, 50, 100, 150, and 200 milligrams what's happening for each patient. And we see largely things that agree with the plot, that at 0, the slope is locally decreasing. At 50, it's becoming more gradual. At 100, it's almost perfectly flat. And then after around 150, the sort of implicit data generating process looks like that. And just to show you how you can set a polynomial with the bin scatter command, you could also do bin scatter, temperature change, mg, line type, quadratic fit. And you can see quite clearly that this seems to do a pretty good job approximating what's going on in the data. The next question that I asked you to do is to construct an interaction term. In this case, it's actually not going to add that much to explaining variance in the data. Let's see, we saw an increase in we saw a very, very minor increase in adjusted R squared on the order of 1%. R squared went up a little bit as well. Or I'm sorry, less than an order of 1%. And I can tell you that this is actually the true data generating process, plus or minus a random normal variable that I did not set a seed for. So sometimes even when you have the right data generating process, you aren't necessarily going to resolve the issues just because of statistical noise and measurement error and things that you can't trace. So what I did was a little bit mean, was to ask you, can you think of other transformations that you might try? Some things that I saw individuals do was add not just a quadratic term, but a cubic term. And that also didn't really make that big of a difference in model fit. Again, the R squared barely moved when we added in this third term, but the adjusted R squared actually decreased a little bit. And finally, and what we're going to be leading into for next week is we're going to talk about how to model non-continuous outcomes. So things like binary variables. Did the patient have an allergic reaction? And what I wanted to show you here was that even when we've got a model that does pretty well, an R squared of 0.64 for one covariate, I think it is a pretty good job. There are some issues when you sort of map things to a linear space. The things that you've got to watch out for are that if you interpret your model as linear, particularly for the extreme values, your linear probabilities might not be that interpretable. That if you're predicting a probability of less than 0, that doesn't make sense. If you're predicting a probability in excess of 1, that doesn't make sense. So what you can do, and you don't have to do it for all situations, but it's something to be aware of, is when you are really concerned about this type of problem and this type of case, you can use something called logistic regression. And what logistic regression does is basically generate an S-curve such that there's a floor and a ceiling to these predicted values of 0 and 1. And the syntax is quite similar. The interpretation can be a little bit tricky because we are no longer measuring linear probabilities. We are instead measuring log odds. But you can see that in this particular case, the associations are similar, that the relationship between increased dosage and allergic reactions are positive. The sort of constant, is less interpretable here, and we'll go more in depth in terms of what it means. This does not correspond to a negative 0.7% probability of negative 0.57, but instead something called a log odd of an event. And we'll talk more about the math and how to interpret that. But just to give you some evidence of that, we run our logistic regression and we can predict these values using the predict command and generate these probabilities. And what we get is a curve that looks like this. So when we plot our logit probabilities on this x-axis and our linear probabilities on the y-axis, you can see that sort of nice S shape. And the logit model, again, on this x-axis is bounded between 0 and 1. And that's nice because you just have probability. You can be sure that your model is going to predict the probability. The other cool thing that we'll talk more about next week is how to interpret these classification metrics. This is probably the closest we're going to get to machine learning, but basically we can look at our linear model, our logistic regression model, and understand how well it's classifying folks. In other words, what's its accuracy? And we see that just this single equation does a pretty good job, that it accurately classifies whether or not a patient is going to have an allergic reaction correctly about 87.5% of the time. And let's just take a look to see how well we do if we were, say, randomly guessing. Well, if we were randomly guessing, and say we always guessed that the patient was going to have an allergic reaction, then we'd be right about 54% of the time. So that's a pretty substantial gain. There are some other metrics that we can talk about. Sensitivity, specificity are different types of accuracy metrics depending on what you really care about. We'll talk more specifically about them, and you'll have some reading on that. But this is your final pre-class exercise and week 4 solution. Thank you so much, and I'm looking forward to seeing you all next week.